Okay guys, in the previous video, we saw that if we have a distributed loading, okay, given by W equals Wx, Newton per meter, the way that we can obtain the equivalent single force acting on that beam is simply by calculating the area under the loading curve, under the curve, okay? So we need to calculate the area under the curve. The area under the curve is the resultant force, okay? That's essentially what we need to take out of that exercise. But the next thing we need to do is determine where along the length of our beam, or whatever it is, where that force is acting, okay? Let's call that X bar. So we've determined how, we've seen how to determine FR by calculating the area under the curve. The next thing is, where does that FR act, the resultant force act? And the simple way to do it is by equating moments, okay? This is a very important principle, which I've discussed quite a bit, is that here we've got a resultant force, okay? And we've got a position of that force, okay? So let's consider point O. So just as we saw in previous discussions, I think it was in chapter 4.8, okay? If we take moments about O, right? And we say anti-clockwise is positive, and we say the resultant moment about O is equal to the sum of the moments about O. You've seen this before, right? When we're trying to determine, if we go back to chapter 8, okay? If we go back to chapter 8, let me just find an example here, right? For example, example 417, as you can see that there's a bunch of forces, and we're trying to reduce it to a single force, like over here, trying to reduce it to a single force, okay? So the first thing we do is we sum up all the forces, but then we need a moment summation. We need to say the resultant, the resultant moment about O is equal to the sum of all the moments of the forces, right? So that resultant moment there, which the resultant force causes about O, is equal to the sum of all the moments due to all the forces, plus this couple moment here. Well, it's exactly the same with a distributed load, okay? Here, we're going to have a ton of dFs, an infinite amount of dFs, right? Acting on a differential element there, okay? So we've got an infinite amount of differential forces acting on this beam, okay? And each of those differential forces is causing a moment about point O, right? Well, obviously not a force acting through point O, but you get the point. You get the point. So we need to equate the moment that the resultant force causes about O. We need to equate that moment with the sum of all of the moments due to all the original forces. But the difference here is that it's a continuous loading, whereas in section 4.8 it was concentrated point loads. So what do we have here on the left? Let me just get back to the correct chapter, 4.9, so that I can work from that. Okay. So this force about point O, we know it's going to be minus FR times X bar. Okay, why do I say minus? Because it's causing a clockwise moment. So that's this on the left-hand side is equal to, what do we have here on the right-hand side? Right? We have, what is dF? So we have dF is an elemental force, okay? And we can have x. So x is the distance from point O to this elemental force that's acting through that element. So x times df is our moment, df is our force, x is our moment arm, and it's also going clockwise, so that is negative, right? That's negative. But we need to sum up all the moments due to the forces. So this is an integral, okay? And then that ultimately ends up being, what is df? Remember that df is equal to wx dx. So we've got x times df, but df is wx dx. So we've got minus fr x bar. X bar is the distance we're looking for. That's the distance that this fr is acting at. Fr is the resultant force, which we calculated by summing the area under the curve, right? Or calculating the area under the curve. And then on the right-hand side, we have the sum of all the moments due to all the forces. But all the forces are represented by differential forces because we have a continuous loading. Each force is multiplied by its moment arm to give us a moment. This df is actually the loading distribution multiplied by the differential width x, okay? Then if you solve for x here, remember, because we're looking for x, let's move that up there. What we end up getting is, we have this x, wx dx, divided by fr, okay? Hope that's clear. But then, that actually should be a plus because minus divided by minus. And actually what this ends up being is, this is simply dA, which is the differential element, and fr is simply dA. Fr is the integral of dA, right? Because remember, fr is simply the area under the curve, okay? So x bar is then simply given by this equation. That's where it comes from. X bar is equal to the integral of x dA divided by the differential area, okay? So that's what we're looking for. How do we determine our resultant force? It's the integral of dA, and that's how we calculate that. It's simply the area under the curve, okay? And then how do we determine our position x? It is given by this equation, okay? So in the next video, I will do 1 or 2 problems. Cheers.